Okay, so here's what we're looking at today. We're going to look at motion on an inclined plane. I gave you a huge assignment for this, 2 problems.
Oh, you made me nervous.
Okay, so what I want to know here, I want to know how fast is this 50 kilogram crate going to be sliding when it hits the bottom of the ramp?
Oh, is it gonna have to be like in 2 parts?
Yes, it is.
Initial.
Yes.
Oh.
Well, it's going to be, I mean, really kinematically there's only one part, but if this is going to be kind of a kinematics problem, right? But if we look at the stuff that we're given initially, kinematically, and let me do something here. How about if I had a good idea?
Whoa.
So let's take this and let's. Uh,
50 kilometers.
Today I was struggling with staying awake.
I can do this.
Is anyone watching American Idol tonight? Brown Billy? I've never seen it. Of Hollywood.
Oh,
No, they're in Hollywood. I don't know. I don't remember those. I'm definitely get that.
you say we're watching American Idol tonight?
Of course.
I'm loyal to my shows.
That's American
Loyal.
Idol. You've seen it every
This is
season.
America.
How long has it been going on?
This is the
15
Too long
years.
is the answer to
This is
that
the
question.
last
this is the
season.
final season.
I
I
thought it ended so long ago. I was like,
15 years or 50
It's
years?
better.
What did they say?
15. Because
50
Keith
years.
Urban's ending, Harry Connick Jr.
Oh my gosh.
I remember watching the one with the Davids, like David Archuleta and David. That was like the last season I actually watched.
That was like
Really-
4th grade.
Yeah, I was so.
Okay,
into it.
so as fascinating as American Idol is, we're gonna talk about physics here. So kinematically, this thing is starting from rest, so we know one thing, right?
Yes.
So V naught is 0. We know the displacement is 9.83, right? And that's it, right?
Yeah.
So if we're trying to find V final, we need something else, don't we?
Yeah.
Yes.
What do you think that something else is?
Acceleration.
Acceleration, okay. Yeah, we need
It wasn't
acceleration.
creepy at all.
If we could fill in acceleration, then we could do this problem, right?
Yeah.
Okay. But how are we gonna do that?
And like the
Do the math.
The FG
Friction.
and MA thing.
Okay, so we're gonna have to come up with, this is where chapter 6 stuff comes into play, only now it's chapter 7, so it's a little tougher. It's not all gonna be convenient anymore. Now the forces that are acting won't all be lined up. Nicely, right.
Yeah.
Is this on Earth?
This is on Earth, yes it is. This is on Earth, good question. So first of all, what are the forces acting on the crate?
Weight.
I've got weight, good. So that's mg, and I've got friction, good. Acting in that direction, right? Okay, anything else?
Normal.
Normal force, yeah. Okay, make sense?
Yeah.
Okay. So what do I do?
Oh, add them tip to tail.
Okay, I need to break it into components,
Yeah,
don't I?
make triangles.
So we need to develop, what is our orthogonal coordinate system going to be here? It's always been x and y directions in the past, but that doesn't work as well here, does it? What do you think?
You can,
Line it up
Like
with the.
with the
Ah,
force
okay,
and the
yeah.
friction.
So parallel to the surface and maybe perpendicular to the surface, how about
Yep.
it, right? So these are our directions. So those are pointing in the positive directions, positive orthogonal directions, right? Those are that's how we're going to define our equations of motion. Let's label these. Let's call this one the parallel direction and that one the perpendicular direction. How about? Instead of X and Y, that's what we're using, okay? All right, so then that works well because 2 of our 3 forces already fall into those directions, right?
Yep.
Okay, what's the one we need to change though? Gravity, okay. So we need to break gravity up into components. Now, what's that gonna look like? So I'm gonna trade my mg vector for components. What do they look like? Okay, do that again, Deshaun. Yeah, okay, so it's gonna come, it's gonna start at the same place. I'm just gonna add them up tip to tail, right? I'm gonna start at the tail of my original vector and I'm gonna end at the tip of my original vector, right? Because I'm really just trading my original vector for 2 orthogonal components. So like that, and like that maybe? Does that make sense? And these are at right angles. Okay? And so what I'm really doing then is I'm just trading like so. What could we call those? We could call this, how about mg perpendicular, good, and this one would be mg parallel, right? Okay, let's call this angle, just so I don't have to write 25 degrees the whole time, let's just call it theta and say theta equals 25. So where is my theta going to be in this triangle that I've created, in this component triangle?
On the top.
Ah, okay, so it's going to be here, isn't it? Right? Now, we could show that geometrically. I don't want to take a ton of time with that, but would you agree that if I look at these triangles, that's a right angle, that's a right angle, and that's a right angle, right? So wouldn't you agree then they're sharing this side, right? If that's a theta, how's that going to work then? If that's theta, isn't this other angle up here, this guy right here is just 90 minus theta, right? Everybody see that? This little angle right here. Because if that's 90, everybody see that?
Yeah.
Okay, so then if this pink angle is 90, and that's 90 minus theta, doesn't that make this little angle up here theta? Because 90 minus theta plus theta equals 90, right? Okay, that's sort of complicated. There's a much easier way to, practically speaking, to do this. Whenever you're dealing with a problem like this, could be an inclined plane, could be a skier on a ski slope, could be anything like that. If the angle is small, it's pretty easy to tell, isn't it? If you draw it at all carefully, you can see that there's a very acute angle and then there's a much bigger angle, right? Well, same thing up here. I just know that the sliver angle goes with the sliver, right? The 2 really small ones match together, and then the 2 slightly bigger ones would match together, right? So if you're doing a problem where this angle is not convenient, like say it's between 40 and 50 degrees, where it looks pretty close to 45, right? What do? Just redraw it. Just redraw it and use the principle of exaggeration, where we're just going to exaggerate the angle by making it small. And then you can always easily tell, oh, so that's got to be theta because that's the small one, right? See what I'm saying? It's a good little trick. Or you can do the geometry if you really want to. Okay, so then we need to draw our free body diagram, right? We're going to draw our orthogonalized free body diagram. The original free body diagram would have just looked like this, right? But we want to draw the orthogonalized one, right? Where we've got only the vectors and components of vectors that fall into these two directions that we defined, right? So that one's gonna look like, oops, like this, right? Still got friction and normal force looking the same. But now we've got a perpendicular component of mg, right? And a parallel component of mg. So what do these equal? If I want to write these now in terms of the parameters of the equation, in terms of theta, what's this one going to be? Let's focus on this triangle up here. mg perpendicular is what? It's always going to be the original vector. If we're looking at a component of a vector, it's the whole vector times what two possibilities? Sine or cosine, right? So you know it's going to be mg times one or the other. Well, which one is this one going to be? It's going to be cosine because it involves the adjacent side and the hypotenuse, right? Okay. And then mg parallel is equal to mg times sine, because that's the opposite side relative to the angle theta, right? Everybody okay with that? So we can make that mg cosine theta and mg sine theta. So that allows us to write our equations of motion, right? This is what we really wanted. That's huge. That allows us to write our equations of motion. So what's the first equation of motion going to look like? Doesn't matter which, I mean, first or second, the order is irrelevant. But what's one of the equations of motion? The net force in what direction? Okay, perpendicular, let's say, arbitrarily, it doesn't matter. The perpendicular component of the net force equals what? Okay, yeah, so there's the positive one, it's the normal force, right? Because that's pointing in the positive perpendicular direction, okay? What? Okay, minus mg cosine theta.
Where are they getting this?
From this picture, right? Because the ones, remember, these are our directions. That's what we call the positive parallel direction, and that's what we call the positive perpendicular direction, right? So we're gonna look at just the perpendicular components and add up all the vectors that have components perpendicular. And the sum of all those is the perpendicular component of the net force, which is equal to mass times the perpendicular component of acceleration. What is that? Zero, because all the motion is parallel, isn't it? Right? Everybody see that? So that one is 0.
How did you get 0 from that again?
Because it's the object is going to slide parallel. It's never going to move perpendicularly at all,
Oh,
right? All the motion is parallel. So then what's our other equation of motion? The parallel component of the net force equals, okay, yeah, we define down the ramp as positive, so it'd be mg sine theta minus friction, and what's that equal? Yeah, m times the parallel component of acceleration, which is all the acceleration, isn't it? Right? Because there isn't any other acceleration. So that's it. There are our equations of motion. That's all we need now, is given these equations of motion, can we solve for A? So this is our unknown that we're trying to find, right? Okay. We got two equations there. How many unknowns can we have? Just fun, I mean, in algebraically, If I have a system of two equations, what's the maximum number of unknowns I can solve for? Two. Yeah. It almost looks like there are three though, doesn't it? I've got one there, I don't know the normal force, and I don't know the friction. Okay, but what is friction equal to? What's our definition of friction?
And mu times.
So mu times
I don't know the rest.
normal force, right?
Uh-huh.
Right? Okay, so we could trade this then. We could write this bottom one because we know, we actually added another equation here, didn't we? F equals mu times normal force. And so now that gives us a third equation that's comes to the rescue, right?
Yeah.
Essentially, we can just make this substitution and the second equation becomes then, all we really care about, we don't care about that part, right? The only parts that we really care about are these parts right there.
Yep.
Right, those are the equations of motion. This just tells us, this gets us started, reminds us what direction we're talking about, right? So now the bottom equation becomes, when we do that, the bottom equation becomes mg sine theta minus mu times normal force equals m a parallel. Okay, we've still got two unknowns in that equation, but what can I do with the first equation? Yeah, I can solve and substitute, right? I can solve for normal force and then substitute, right? Everybody see that? So up here I get normal force equals mg cosine theta, right? And I can just make that substitution. So I end up with mg sine theta minus mu sub k, I guess, times mg cosine theta equals ma, right? Parallel, I guess. Okay. How many unknowns in that one? One. Down to one, aren't we?
We borrowed the link.
And you.
And me.
You later.
Okay, Delaney.
I need a picture of you and your dad.
Oh.
Okay.
That's why Lily said, oh.
Okay, so what about that is interesting? You see anything we can do to make this simpler?
It's independent of that.
Ah, look, I could divide a mass away from both sides of the equation, couldn't I? Everybody see that? Is that, Libby, do you have a question?
Oh, she.
Is that answered? Okay. So we could divide both sides by m. So what does that tell us? If the m divides away from both sides, that's huge. What's that tell us?
Does that factor into the?
Independent of mass. Yeah, it doesn't make any difference what the mass of the crate is. Okay? So then, what else could we do? Well, we could, I like this. Is there anything we could do to the left side, algebraically? You could factor out a g, couldn't you? G is a common factor. So we could write the left side as g times sine theta minus mu cosine theta, and that equals a. Okay, that's interesting to me in a way. I like to look at things like this because if you look at this from a physics perspective, that's telling you something interesting. It tells us that the acceleration of the crate is really just the acceleration of gravity times this other factor, right? Now, what are the parameters of that other factor? In other words, what are the things that affected it? If we go back and look at our picture, if I took the extreme case that this angle were 90 degrees, would you agree just by, kind of thinking about this, wouldn't the acceleration just be gravity in that case? Right? Does that make sense?
No.
Okay, but it's not in this case, right? We back that angle down to 25 degrees. It's not 90 degrees, and so the acceleration is going to be diminished. How is it being diminished though? What are the components? Or not components, that's a bad word. What are the parameters that are affecting how much G is diminished? So and not that sine or cosine are just functions, but it's the theta, right? So it's the angle of inclination of the ramp and frictional coefficient. Doesn't that make sense? The steeper the ramp, the more acceleration you're going to get. So you should see thetas in there, right? And it should be impacted by the friction too, right? By the coefficient of friction. So the math gods are pretty smart. They tend to take care of this stuff for us, right? So we know that all the stuff is in there that should be. Now really all we have to do is just plug and chug, right? So we know these values. We can plug in and see what we get. So we're going to get about, what, 9.80 times sine, wasn't it 25 degrees? Minus, what was the coefficient of friction?
0.320.
320?
Point.
Oh, what am I saying? Of course, yes, that'd be a pretty big coefficient of friction, wouldn't it? Equals what?
Let's do bingo.
Be small.
So we didn't have to put in 9.83 ever, or will we have to?
Oh, we haven't yet.
Okay.
Haven't yet. So what's that about? 1 point something?
1.299.
So
Oh, yeah,
1.30
Yeah.
out to that many places. Oh, great, thank you. I'll take that. All right, thanks. Okay, and we'll just keep that in our calculator out more, keep all the unrounded number. But now we know what the acceleration is, so now we can go back to this stuff, right? If we know the acceleration, this gets pretty simple. All we're trying to do is find v, right? So what's the kinematics equation we're going to use?
B minus B, yeah, B squared minus B naught squared.
The non-t one, good. Right, so we get v squared minus v naught squared equals 2a delta d. That's 0, right? So v is just the square root of 2a delta d. So the square root of, let's see, so that's going to be 9.83 times, 2 times, so 2.6. I'll just combine some stuff. I don't know why I did that, right? Whatever that was. So what is that roughly?
5.05.
5.05. I think we get to keep, I guess we could keep all that, don't we? So 5.05 meters per second. Did I plug in the right stuff there? Looks like I did.
Yeah.
9.83. Yeah, okay. That's it. How about that? Okay. Make sense? Okay. We got a little time, so
Wait, how do you get these equations?
how do we,
How do we, never mind.
that's right, what are you looking at, Delaney,
How
down
did
here?
we get Fn minus n, how did we get the F net equation? It
This-
was like in our notes. Oh,
Get these
okay, I see.
from the free body diagram.
Okay.
Okay, and all that makes sense? Any questions on that? Okay, so let's look at we're getting pretty close to wrapping this whole, I'm gonna give you an assignment over this stuff, and then I'll give you a separate assignment over projectile motion. But let's take a quick look at projectile motion. We can at least, projectile motion is easier than this, seriously.
Good.
Projectile motion is, it seems like it'd be very complicated, but it's not. Projectile motion And I'm gonna put a little fine print on this. Without friction. So we're gonna coat our projectile with slip rim, right? So it just slides through the air with no friction, right? So if you think about projectile motion, once, like let's say we're gonna shoot a golf ball out of a, golf ball gun, and the golf ball is coated in slip rim, and let's say that it's phosphorescent and it's at nighttime, so we can see this thing really well. If you are high above, hovering in a blimp, and you're looking down at this point of light that the golf ball represents, and you're watching the arc of this thing from above, what are you gonna see?
Just
It's gonna be a straight line. What else about it?
The dot might get a little bit bigger.
Maybe a little bit. Something else important about its motion though.
It's gonna change its speed.
It changes its speed because the ball's going slower at the top.
Yeah.
Okay, let me ask you this. After the golf ball leaves the gun, what are the forces acting on
Gravity.
it? Just gravity, right? Oh yeah, okay, so if we look at our golf ball then, our golf ball, the only force acting is mg. What's our coordinate system gonna be probably for this one? XY. So the only force is acting vertically, therefore the only acceleration is vertical, right? Okay, the net force horizontally is what? What's the value gonna be of the net force horizontally?
However, when you blew it out of the can.
No, it's always the same answer. 0. There is no, this is our free body diagram, right? There is no force acting horizontally, so the net force, that's a pretty boring equation. The net force, if we were to write it,
But how is the gun not accelerating it forward?
well, while it's in the gun, that's different. While it's in the gun, there's something's pushing on it. But once it leaves,
That's just going.
it's just going. Now it's in free fall, right?
Okay.
And so the net force horizontally is just 0, right? It's just ma sub x, and it's 0, right? There are no forces to add up, no components, right? So I'm going to ask you again, what's this thing going to look like from above? Mm-hmm. You're looking straight down on this thing. You can see it traveling in a straight line at a constant speed. How come constant speed? Because there's no acceleration horizontally. How about that? So if you look at the characteristics of projectile motion, one thing is v sub x is a constant. The horizontal component of velocity is constant for projectile motion. Seen from above, the thing just travels in a straight line at constant speed. What if you're looking from far away, you're looking at this thing, so you're on the ground watching this thing go up in the air towards you. What's it going to look like from that perspective? Where you're isolating the vertical component of the motion, in other words. Right? You can't see the thing moving horizontally, you only see the vertical part. Well, it's going to go up and down probably. It's going to be the very same thing you'd see if somebody just took the golf ball and tossed it up in the air and caught it, right? Because you can't see the horizontal motion anymore. So vertically speaking, this is just like all the examples you guys have already dealt with in the kinematics chapter, right? Where we threw a ball up in the air and caught it, right? Okay? All right, so then let's do a problem. We're going to start off with one that's kind of an easier one. Here's our problem. This is a 50-meter high cliff, and we're going to shoot the golf ball off the cliff with an initial velocity of 70 meters per second, horizontally. Okay? I want to know how far away from the base of the cliff is that golf ball going to hit the sand on the flat plane below. Okay? Can we do this?
Yeah.
We can. There's our initial velocity vector. Let's break it into components. Done. What's the vertical component of the initial velocity? 0. There is no vertical initial velocity, right? It's all horizontal.
Wait, why doesn't gravity count?
It does. But the initial velocity, when it leaves the barrel of the gun, right? If we were looking straight on, all we would see in this case is it'd be just like somebody's dropping a golf ball, wouldn't it? If we're looking from far away and it's coming at us, right? Okay? So let's break this up into two parts. Let's break this up into the x components
What are we figuring out where?
and the y components. Our goal is we want to see how far it travels before it hits the ground. Okay? So horizontally speaking, so we're looking at the x stuff. Horizontally speaking, what is the initial velocity? So v naught sub x is 70. Good, standard units, right? What else do we know horizontally? I guess we know that the initial position horizontally we'll call 0, right? And we're trying to find that, right? How far it travels horizontally, d sub x. But we can't solve that, can we? Not enough information. We need something else, right?
Mhm.
So where are we gonna get something else?
Don't need time.
Time would help, wouldn't it? Time would be great. If we had time, that would be wonderful. Okay. Where could we find time?
Why?
Oh, let's look at the vertical motion. Okay, vertically speaking, we know that, let's see, the initial velocity vertically is what? 0. There is no component of the initial velocity vector, vertically speaking, right? We know that the initial position is, call it 50, and the final position vertically is what? 0. Okay? We know what the acceleration is vertically. What's that? So down, so negative 9.8?
Yep.
And that's a lot of stuff. So we could find t, couldn't we?
Yeah.
And wouldn't you agree that the time it takes for the golf ball to hit the ground vertically is the same time it takes for the golf ball to hit the ground horizontally? It's the same golf ball, right?
Hopefully.
Yeah. So what's the equation we would use here? And this is the Big Daddy, isn't it? So we gotta use the d equals d naught plus v naught t plus 1/2 at squared with our vertical stuff, right? So what do we get then? If we plug that stuff in, we get 0 equals 50 plus 0t, right? Plus 1/2 times negative 9.8 is negative 4.9 t squared. Okay, so that means t squared equals 50 over 4.9. So t equals the square root of 50 over 4.9, whatever that is. But we'll just add that to our list over here, right? What equation are we going to use on this side to solve for d? Yeah, we just use the first one, couldn't we? Right? We could use the one d equals d naught plus v bar, and v bar is the same, right? It's constant velocity, so the average velocity is just the velocity, right? V bar t, d naught is 0, so we get d equals 70 times t, which is the square root of 50 over 4.9. So what's our answer? 223, so to two places, 220. How about that? You got it. Not so hard, huh? what's the main points here to kind of keep in mind when you're doing these problems? Well, we're just breaking it up into components, right? We've got a horizontal component and a vertical component, but they describe the same object. And so the parameter that they always are gonna share is t, isn't it? Right? So if I'm trying to find out what trying to find some quantity at the end of the movie, I just have to be able to find, okay, that's gonna happen at a certain time, and then I can maybe solve for that time on either the horizontal or the vertical column and plug it into the other one, right? How would this problem have been a little bit harder if maybe the initial velocity vector had been changed? Let's say the initial velocity vector, instead of being straight, what if we launched it up a little bit? So V naught was maybe inclined at a 30-degree angle. What would I have done differently then?
You have to break
You
it
have to
into
break
two
those
parts.
up.
Yeah, I would just break the initial velocity up into components, and I would get some number up here that would be different than 70, right? I would get some number, some number for the x component of the initial velocity, and some number for the y component of the initial velocity. But otherwise, it would be the same problem, wouldn't it? Okay? Make sense?